All right, so welcome back to our chemistry flipped classroom. And today we're discussing the arrangement of the electrons in the atoms. So this has to do with our quantum model of the atom. And what we're specifically addressing is what we call electron configuration. So the goal of electron configuration is to have a sort of shortcut expression to tell us where all of the electrons are. And so we're just going to really quickly review the quantum configuration, review the orbitals. So we know that we have this principal quantum number. That's the overall energy level. And our energy levels go from 1 to 7. So we have this principal quantum number. That's our energy level. It tells us something about the size of the orbital. The smaller the number, the smaller the size of that orbital. And if we are to square that principal quantum number, that tells us the number of orbitals in the energy level. Okay, or suborbitals. Then we have our orbitals, which we know we have S, P, D, and F. And so our S orbital is shaped like a sphere. Our P orbitals are shaped kind of like an hourglass or a peanut. Our D orbitals are shaped like essentially double P orbitals, except for the one that's a P orbital with a ring around it. And then we have the F orbitals that are shaped like flowers. And we remember that these are all really sort of overlapped, superimposed on each other. We pull them apart so that we can look at their structure, but we know that they actually all overlap and exist on top of each other. And so this is what it would look like if we imagined them all put together. And we know that each suborbital, so each p orbital, each d orbital, each s orbital can hold 2 electrons. We know there's 1 s orbital, 3 p orbitals, and 5 d orbitals, and 7 f orbitals. And we also know that if there are 2 electrons in the same suborbital, that they are spinning in opposite directions to minimize that repulsion. So we know how to fill our orbitals. We're going to talk just a little bit about Hunds Rule. So Hunds Rule tells us that if we have orbitals that have equal energy, so if we have 3 p orbitals or 5 d orbitals, all at the same energy level, they're each going to be occupied by 1 electron before any of them is occupied by a second electron. So we go back to that analogy of if you guys all go to get on a bus, everybody's going to take their own seat. It's not until we run out of empty seats that you would double up in a seat. And so electrons are the same way. They're repelled by one another. And so if there is an empty orbital, they're going to go into that empty orbital of the same energy level. Now, remember, they're also lazy. So they're not going to go to a higher energy level until all of them are full. All the electrons that are in singly occupied orbitals. So if we have 3 electrons in our 3 individual p orbitals, they're all going to have the same spin. So we're going to represent that with arrows pointing the same way. So let's take a look at how we do electron configuration. So here's a few of our early elements, and we have configuration notation and we have orbital notation. And I like using orbital notation because I think it helps you to visualize where those electrons are. So if we look at lithium on the periodic table, we can see that it's element number 3. So we know that that means that it has 3 protons and 3 electrons. And so we know that the first 2 electrons are going to go into the 1s orbital because that's the lowest energy orbital. And then that third one is going to go into the 2s. And so you can see in our orbital notation that we represent that with an up and a down arrow in the 1s and an up arrow in the 2s. And in our electron configuration notation over here, we write that in our 1s orbital, we have 2 electrons. And in our 2s orbital, we have 1 electron. And then we have this shortcut notation over here that we call noble gas notation. And noble gas notation is the idea that we can say, okay, well, lithium has all the same electrons in all the same places as helium. And then it also has one more electron, and that one more electron is in the 2s orbital. So we can do the same thing with beryllium. We're going to look at orbital notation. So again, we're going to have an up arrow and a down arrow in the s, 1s. And now we're also going to have an up and a down in the 2s. And so we would write this as 1s2, 2s2. And our noble gas notation, again, it has all the same electrons as helium, the noble gas before it. And then it has 2 more electrons in the s orbital. And then we move on to boron, and we look at boron on the periodic table. We can see that it has 5 protons, so we know it has 5 electrons. So we're going to put those same 2 in the 1s, 2 in the 2s, and now we have to move to the 2p. So it's important to recognize that we fill the 2s orbital before we move to the 2p orbitals, because the 2p orbitals are just a little bit higher than the 2s orbitals in terms of their energy. And so we continue on doing the same thing, but I wanted to go ahead and jump ahead here to oxygen. So when we get to oxygen, now we have enough electrons that we have to add that 4th electron into the p orbitals. And so we put 1 electron in each of the p orbitals because they're all the same energy level. And then we come back and we put a 4th one in one of the p orbitals. Our convention is to put it in the first one. It doesn't really matter. And so we write this as 1s2, 2s2, 2p4. But I want to take a step back because I think you guys can write these and show you when we look at the periodic table that we can write the electron configurations just from looking at the periodic table. So in these first 2 columns, the valence electrons are going into the s orbital. And in these last 6 columns, the valence electrons are going into the p orbitals. And so we can just count over into that block. So let's say if we look at phosphorus, it's in the 3rd row, 1, 2, 3, and it is 3 blocks into the p orbitals. And so we know that this is 3p3. And then we could just backfill all of the electrons that come before it. Or we could write this in a noble gas configuration where we would say that this is just like a neon. We would put the square brackets Ne in square brackets. And then the 3s2, 3p3. So we have a lot of different options for doing this. Here's our overall orbital filling table. And you can see that we have the S block here, the P block here, the D block here, and the lanthanides and actinides, which are normally pulled out underneath the periodic table, are the F block. So I know this is a lot of information. We will go over this in class, but I wanted you to have an introduction to it before we jump in class. As always, I look forward to seeing you in class. If you have questions, let me know.